because the mass difference is still 1, okay, still 1 between carbon-12 and carbon-13, but now the charge is 2. Okay, this is a doubly charged species. So the distance between these on the mass-to-charge scale is going to be 1/2. And that's very useful information because it allows you, if you don't know what you're looking at, you can calculate what is the mass of the peptide. So, because you can work backwards, okay. So if we look at the spacing between the isotope peaks, we know what the charge is. Because if the spacing is 1, then the charge is 1. If the spacing is 1/2, then the charge is 2. If the spacing is 1/3, then the charge is 3. Okay. So we know that this is a doubly charged species. So we want to work back towards the mass of the neutral molecule. Then we need to multiply the mass to charge by 2, okay, because we know the charge is 2. So if we want to work out what the mass is, we've got to multiply it by 2. And then we need to subtract the mass of the 2 protons. Okay, so that's it calculated for this particular species, okay. So it appears at a mass to charge of 591.79. We know that's doubly charged because of the spacing. So we need to multiply it by 2 and then take away the mass of those 2 protons. Okay, and if we follow that through, that gives us 118.51, sorry, 0.58. And if I just skip back to that previous slide, where it shows you the neutral mass of the molecule. Does that all make sense? Yes? Okay. Right, so this is ubiquitin, which has got a mass of 8.5 kilodaltons. Okay, so it's electrospray spectrum. So we talked about this last time. What you see is this distribution of different charge states. Okay, so these are ubiquitin ions with 6 protons, with 7 protons, 8, 9, 10, and so on. If we focus in on the 6+ peak, this is what we see. Now again, each of these peaks corresponds to an isotope peak. So this one here is the species where all the carbons are carbon-12, and here we've got 1 carbon-13, 2 carbon-13s, 3 carbon-13s, and so on. Okay. And so what's the distance going to be? What's the spacing between these peaks? Yes, it will be a 1/6, 1/6, that's right, yeah. Okay, so you might notice that this distribution looks a bit different to what we were looking at on the previous slide, where the carbon-12 peak was the most abundant. But the bigger the molecule gets, so the more carbons there are in it, the more the likelihood that one of those carbons is going to be a carbon-13. Okay, so you start to see a shift in the distribution of the isotope peaks within a particular peak. So that's why it looks different. Okay, so the spacing here is 1/6. If we looked at this peak here, the spacing would be what? If it's 12 plus. 1/12, yeah, exactly. Okay, so here's a quiz for you to have a go at. What's the neutral mass of these molecules here? We see these in the spectrum. And then what would the mass to charge be of these ones? So I'll let you think about that for a minute and then we'll go through them. just while you're looking at that, who's got the register? Where's the register? Has everybody signed it? Has everybody signed the register? No? No? Right. Okay. I can see it back there. Bring it forward. Has everybody got an answer for these? Yes? Good. Okay, so what's the answer to the first one then? If you've got a mass to charge of 371 and an isotopic spacing of a third, what is the neutral mass of the molecule? Say it again. Did everybody get that? Yeah, okay. So you calculate it by multiplying by what? 3, yeah. And then you have to remove the mass of the 3 protons that are given it that charge. Okay. How about this next one then? This one's a bit easier. Neutral mass is... Somebody shout out. 520. Did everybody get that? Yeah, okay. So you know it's singly charged, so you just need to remove the mass of the 1 proton. And what about this third one then? Yep. Did everybody get 2,406? Good. Anybody not get 2,406? No? Okay. Right, so then the bottom ones are what's the mass to charge. So if you've got a singly charged molecule of mass 246, where would you see it in the mass spectrum? Yeah, 247. And then a doubly charged molecule of mass 649. Somebody different shout out. Somebody from over here. Go on. Have you worked it out?
Yeah, 325.5.
Yep, did everybody get that? Did somebody say no then? Okay, so if you've got a neutral mass of 649, you need to add on the mass of 2 protons and then divide it by 2. Okay, that will give you 325.5. And then this last one, okay, so an 8 plus ion of molecule of mass 1945. Did you get 244.13? No. Okay, so you need to add on the mass of 8 protons. Okay, so add on 8 and then divide it by 8. Okay. Oh, there we go. Okay. Right, so this slide is included to sort of demonstrate to you the importance of the resolution of the mass spectrometer. If you're looking at a large molecule, or quite a large, myoglobin is about 16 kilodaltons. And if you look at the 21 plus charge state with the QTOF, that's what you would see. Whereas if you look at the same species on an FTICR, this is what you get, okay? Because the FTICR has got much better resolution than the QTOF. With the FTICR, you're able to see each of the individual isotopic peaks, okay? And so what's the spacing going to be with these? So 21 plus charge state. 1/21, yeah, so that would be the spacing. With the FTICR, you can see that, but you don't get that information with the QTOF because you can't see the individual isotope peaks. So you wouldn't be able to calculate, as we've just been doing, the exact masses of them based on that peak at the top there. Okay, so, I mean, last time I was telling you how great mass spectrometry was and it's going to solve all the problems. On its own, mass spectrometry just measures mass, okay? So if you've got a peptide, or another analyte, if we're using it for something else, all you get, all the information that you get is the mass to charge of the intact molecule, okay? Which is great and can be very useful, but it doesn't give you any structural information. And that's really what you're after when you're doing proteomics, because we need to be able to work out what is the sequence of that peptide. Okay? So we need to get some structural information. And I'm talking about primary sequence, a chemical structure, rather than a 3D secondary, tertiary structure that you would associate with proteins. So we want to find out what the primary sequence is. And the way we can use mass spectrometry to do that is to use tandem mass spectrometry. And this shows the workflow for that. So the first step is mass analysis of the parent. So that would be the peptide that you're interested in. What's its intact mass? Okay. Then you select that peptide. So you throw all the other peptides away that are in the mixture and fragment them and look at the mass of the fragments. And the idea is that from looking at the mass of the fragments, you can piece back together what was the molecular structure of the parent ion, the ion that you started with. And I'm going to use the phrase intact mass a lot and talk about precursor ions, but always remember that what I'm talking about are those proteolytic peptides. So when I say the intact peptide, I don't mean the protein. Okay? The protein's already been digested into peptides, and we're looking at the mass of the peptides, and then we're looking at the peptide fragments. So you can do tandem mass spectrometry in space. So the two parts of the analysis, the mass analysis or the selection of the precursor ion and the mass analysis of the fragments, are separated in space, or they can simply be separated in time. Okay? So the top one is an example of a spatial tandem mass spectrometry. So you'd have two separate mass analyzers coupled together. For example, QTOF. And so mass analyzer 1, MS1, is where the parent ion is selected, and then fragmentation takes place, and then the fragments, the masses of the fragments, are measured in the second mass analyzer, MS2. Now, if we use something like an ion trap, which we were looking at earlier as a type of mass analyzer, we don't have multiple mass analyzers, but we separate those processes in time. Okay, so we trap all of the ions in the ion trap, measure the mass of the parent ion, the precursor peptide, throw everything else out, and then fragment the ion, the parent ion, in the ion trap, and then measure the mass of the fragments, still in the same place, still with the ion trap. Okay. But it's the same idea. You start with your peptide, you select that, you fragment that, and then you look at the product ions. Okay, and you could use different instruments, as I was just saying, for doing tandem mass spectrometry. So tandem mass spectrometry is often written as MS-MS, okay, and I've used that notation here, and you'll sometimes see it as MS2, okay, but they're the same thing. Yes, so you can separate the space. You could use a triple quad, or you could use a quadrupole time of flight mass spectrometer, or in terms of temporal, the ion trap I was just talking about, or the FTICR. Now, the advantage of doing this is that you could do multiple stages of mass spectrometry. So you could start with your peptide, fragment it, and then take one of those fragments and fragment them further. Okay? And that opportunity is available to you if you use a temporal approach. But if you use a spatial approach, you need another mass analyzer. Okay, so you've got MS1, and then you'd have MS2, and then you'd need MS3. Okay, so it's not really feasible to do that. There are a number of different ways in which fragmentation can be induced. The top one is the most commonly used, so it's collision-induced dissociation, and you'll also sometimes see it written as collisionally activated dissociation, so CID or CAD or CAD. And you tend to find, if you look in the literature, that it's the UK European papers that use CID, whereas the American papers tend to use CAD or CAD. Okay. But I think as time goes on, I think CID is winning. I think you'll probably see that more commonly used. But don't make the mistake of thinking they're two different things, because they're not. They're the same idea. So the idea behind CID is that your ion, your precursor ion, so peptide in this particular case, is accelerated and collided with an inert gas. Okay, so it increases its kinetic energy and it collides with an inert gas. Now, the collision is inelastic, and so some of that translational energy is converted to internal energy of the peptide. Okay? And that energy is distributed throughout the molecule, will build up with multiple collisions, and eventually you'll get cleavage of the weakest bond. In a peptide, that's the peptide bond. Okay, so the amide bond cleaves. Now, another method of inducing dissociation is surface-induced dissociation. Okay, and this has been quite, I guess, overlooked as a technique for a number of years, but it is becoming more and more commonly used in proteomics now. Okay, and the idea is very similar to collision-induced dissociation, except rather than having an inert gas, which the peptide ion is collided with, you've actually got a surface. Okay. But the principles are very similar. So still in an inelastic collision, you get some of the translational energy converted to internal energy, and then ultimately the weakest bonds will cleave. Another option that's available is infrared multiphoton dissociation, or IRMPD. And this involves firing an IR laser at trapped ions. Okay, so it's limited to the types of mass analyzer that you can do IRMPD on. It has to be either an ion trap or an FTICR, something where the ions are trapped. And again, it gives you similar fragmentation patterns to CID and SID. And then lastly, we've got these two, electron capture dissociation and electron transfer dissociation, which are the newest developed fragmentation techniques. And they involve transfer or capture of an electron by the peptide. And so, first of all, you need to have multiply charged ions, because if you had a singly charged peptide that captured an electron, then you would have a neutral, and then that's no good. You can't see that in the mass spectrometer. So you need to have at least a doubly charged peptide that can capture or have transferred to it an electron. But as a result of the transfer or capture of the electron, you've got an unpaired electron, so you've got a radical species. And then you get some radical chemistry occurring, and so you don't necessarily get cleavage of the weakest bond. I'll show you that in peptides you get a cleavage of a different bond. But it's quite useful, or ECD and ETD are quite useful if you are looking at peptides which are post-translationally modified, particularly by something very labile like phosphate or glycosylation. Because remember when I was talking about CID, it says it cleaves the weakest bond, which generally speaking is the peptide bond. But if you've got a phosphorylation on there, that will be the weakest bond, and that will be what's lost. So you won't get sequence information, you'll know that you've got a phosphate there. That's not the case with ECD and ETD. Okay? Because they don't cleave the weakest bonds, then the fragments that you see will still have that phosphorylation attached. So it allows you to determine the sites of modification. But they're not as efficient as CID, so generally speaking, CID is the first technique that gets turned to. Okay, so if we do CID of peptides and proteins, and then we'll assume that they're not modified, okay, so it's an unmodified peptide, and we get cleavage of the weakest bond, okay, which is the peptide bond. So on these schematics, the circles are meant to represent different amino acids. Okay, so a different colour, it's a different amino acid. So if you concentrate on the tanned one, okay, so if this was a peptide, each of these are different amino acids. We'll get cleavage at, say, between the pink and the grey amino acid, okay, which would give us 2 fragments, as shown here. And they're termed B and Y fragments. So the B fragment contains the N-terminus, and the Y fragment contains the C-terminus. And then they're numbered from those termini, okay? So this here is the B4 because it's got 1, 2, 3, 4 amino acids in it. This is the Y5 because it's got 1, 2, 3, 4, 5 amino acids in it. Okay, so they're numbered from the termini, and they're named for the termini which they contain. Okay, and so you would also get cleavage here, okay, between this grey and pink amino acid. That would give you the B3, so 1, 2, 3 amino acids, and the Y6, 1, 2, 3, 4, 5, 6. Okay. So what sometimes can be a bit confusing is that you just get one cleavage per peptide. Okay. So when you're doing mass spectrometry, you're looking at a population of ions. So if you've got one particular peptide, okay, you may be looking at 1,000 ions. Okay. So there'll be 1,000 of those starting peptide ions. And some of them will cleave here. So some of them will cleave here, and some of them will cleave here, and some of them will cleave here. So you get this population of fragments. Okay, so there'll be some B3, there'll be some B4, there'll be some B5 that have come from various places. Okay, so don't think of it as just a single peptide molecule. There's a whole bunch of them there. There's a whole population of them. Okay, and we can calculate or deduce what the sequence of the peptide is by looking at the mass differences between the fragments. Okay, so if we looked at the mass difference between the B3 and the B4, it would correspond to the pink amino acid. And so then if you get another peptide which comprises the same amino acids but just in a different sequence, you will get different B and Y fragments. Okay? So in this example here, we've just swapped the 3rd and 4th amino acids around. Okay? Okay, so the mass of the B4 from this peptide is the same as the mass of the B4 from this peptide. But the B3 masses are different. Okay? So that allows us to tell that they've got different sequences. Okay, and I think that the next slide is, yes, so this is a real example. Okay, so this is the CID spectrum that was obtained for this peptide here. Okay, so when it was fragmented, all of the precursor ion has gone. Okay, so it's all been broken up into the fragments. So we don't see a peak in the mass spectrum that corresponds to the precursor ion. But we've got this peak here, and that corresponds to the Y7. Okay, so the mass difference, which is this cleavage here, okay, between the isoleucine and the alanine. So it's this part of the molecule. Okay, so the mass difference between that Y7 fragment and the precursor, which we've measured previously, but we can't see now, that corresponds to the mass of the isoleucine. And if we move down to the next peak, which is here, so this is the Y6, okay, so cleavage here. The mass difference between the Y7 and the Y6 corresponds to the mass of alanine. Okay, and so you can work all the way down, okay, looking at the mass differences between these peaks, and they tell you where are the different amino acids. Yes? Ask me again.
Does it matter whether you're counting from the C terminus or the N terminus, or is it just arbitrary? Like here you've counted the Y, but would it matter?
Well, okay, so I have counted the Y. The reason this particular peptide, and in fact most peptides that we're going to come across when it comes to proteomics, because we use trypsin as the enzyme, the resulting peptides have all got arginine or lysine at the C terminus, because that's where it cleaves. Okay? Which means that if this is a singly charged peptide, the charge is likely to be on the arginine or the lysine, okay, because they're the basic amino acid residues. So that's where the charge is going to go. And because when we use trypsin, the lysine or arginine is always at the C terminus, that means that what we get are Y fragments. Because the Y fragment is the fragment that contains the C terminus. So the complementary B fragment doesn't have a charge, and so we can't see it. Okay. So in this particular example, we're only seeing Y fragments. Now, sometimes you do see B fragments, especially when we're looking at a singly charged precursor here. If we're looking at a doubly charged precursor, okay, one of the charges is going to be on the lysine or arginine, and one of the charges is going to be somewhere else. Now, generally speaking, the other charge will be on the N terminus. Okay, so then if you get cleavage, you are likely to have a B and a Y fragment. Yeah? Does that make sense? Not really. No. So if you have a peptide and it's singly charged, so there's one proton on it, but it's from a trypsin proteolysis, all of the peptides are going to have lysine or arginine at their C terminus. And that will be where the charge goes, because those are the basic amino acid residues. Okay? So when the peptide cleaves, okay, so if it cleaves here, actually, if it cleaves here, right, you should have a B2 fragment, which comprises the isoleucine and the alanine, and a Y6 fragment, okay, which comprises this. But remember that the precursor only had one charge, okay, and it's likely to be on the arginine because the arginine is basic, which means you won't see the B2 fragment because there's no charge there. And it's a mass spectrometer and it needs to be an ion for it to be able to be picked up. If you had this peptide and it was doubly charged, so 2 protons on it, one of the protons would still sit on that arginine because it's still the most basic residue, okay? But the other charge would have to go somewhere, right? And the most likely place is the N terminus, because that nitrogen and the N terminus is the next most basic place, okay? So then, when you've got fragmentation here, this is a doubly charged, so you've got a charge on the B2 fragment and a charge on the Y6 fragment, and you'd likely to see them both. Okay? Yes?
I guess I'm confused about you must have this application. Why can't you just analyze the entire thing as one charge?
Because if you look at the intact, if you just measure the mass of the intact peptide, you've got no information about the sequence. But because you've got all of these fragments, you can work out what the sequence is. Okay, so that'll give you the confidence in what you're eventually the protein that you're assigning. So you need to know the sequence.
So essentially, you digest the protein and then you fragment it and you essentially get the entire sequence eventually.
Well, yes, except you don't need the entire sequence to be able to identify the protein. Okay. Yeah, you don't need the whole lot to be able to identify the protein. We've got a quiz that we'll do probably next time, So I don't think we're going to reach it this time. Which will show you why you don't need to see the whole sequence. But yes, that is the idea. So you take the protein, you cleave it up into peptides, you take the peptides and then measure them by mass spectrometry and fragment them to get the sequence of the peptides, and then you piece that all back together again to find out what the protein was. Yeah? Okay. Right, so I was just drawing coloured circles on a piece of string as an illustration for a peptide, but of course they've actually got a molecular structure. Okay, so this is a model tetrapeptide. When you do CID, you get cleavage of the peptide bond, so you get a Y ion, which contains the C terminus, or a B ion, which contains the N terminus. How are we doing for time? All right. So the structure of a Y ion is that of a truncated peptide. Okay? So you've got this linear peptide structure. Okay. The structure of a B ion, however, is cyclic. Okay. You'll note when I was talking about the previous slide, I said we'll talk about B2 ions, not B1 ions. And the reason is you don't get B1 ions. Because of this cyclic structure, you need at least 2 amino acids. Okay, so you never see smaller than a B2. So you see B2, B3, and so on, but you wouldn't see a B1. Okay. So if you wanted to work out the mass to charge of your Y ion, it would be the masses of the individual amino acid residues plus the termini. Okay, so if we use this example here, okay, so we've got this tetrapeptide, glycine, threonine, proline, arginine. Okay, and we wanted to look at the Y3, so that's the cleavage here. To calculate the mass to charge of that, we take the mass of the threonine residue, the mass of the proline residue, and the mass of the arginine, plus we'd need 1 for the hydrogen that's at the N terminus, plus the 17, which corresponds to the OH at the C terminus, so here and here. And then obviously it's charged, so we need the mass of the proton. Okay. Now the B ion is a bit different. Because it's got this cyclic structure, you don't need to worry about adding on the mass of the hydrogen at the N terminus or the OH group at the C terminus. Okay. If you want to calculate the mass to charge of the B ion, it's just the sum of the amino acid residues plus 1 for the charge. Okay, because it's cyclic, you don't need the hydrogen and the OH group. Yes?
So is all B ions cyclic?
Yes, yes, they're all cyclic, yes. But they don't... It's only the last 2 amino acids that form the cyclic part of it. So if you had a B4, it wouldn't be a big ring of 4 amino acids. It would be a ring of 2 and then the tail of 2 and so on. Yeah. But because of that, because you've got that cyclic structure, that sort of negates the hydrogen and the OH group. Yes? That's a very big question. That the chemistry of when it forms is that it will cycle back on itself. You can draw some curly arrows if you want.
Okay, so this is part of the breakage.
Yeah. Okay, so the B3 ion, again, of this tetrapeptide, so B3 would be between the proline and the arginine, would be the mass of the glycine, the mass of the threonine, and the mass of the proline, just plus 1 for the charge. Okay. Now, I think we are at 10 to 5, so we should probably stop. We'll just do these. So if you've got this peptide here, okay, so threonine, serine, tyrosine, arginine. The B2 fragment would be the fragment that contained the threonine and the serine. So if you're calculating the mass to charge, I've given you the amino acid residue masses here. Okay, so it would be the mass of threonine plus the mass of serine plus 1 for the charge, okay, because it's cyclic. If it was the Y3 fragment, so that's cleavage between the threonine and the serine, you've got the mass of the arginine, the tyrosine and the serine, plus the hydrogen at the N terminus, plus the OH at the C terminus, plus the charge, which gives you a mass charge of 425. And then lastly, it's maybe not a great way of writing it, but I'll go through it anyway. So if you want to work out the mass to charge of the same Y3 fragment, but this time with a 2 plus charge, okay, so we've already worked out so far what the mass of this plus 1 proton is, but we need to add on another proton and then divide it by 2 to give us 213. So it's essentially this part, except here, because we've got 2 charges, we add on 2. Okay, and then we have to divide it by 2 because we measure mass to charge. Okay, so we'll stop there then, and we'll see you next Tuesday for quite a lot of the day next Tuesday.